Welcome to another video for Stat 212. In this video, we're just going to do some probability practice. So I'm just going to kind of work through these two problems on this particular page. So here we have a fictional poll with 911 people over the age of 65. 59 of the individuals in this survey had lung cancer, of which 38 were current or previous smokers. The remaining 852 people in the study did not have lung cancer, of which 192 were current or previous smokers. So first we're going to go ahead and fill in these missing cells in the table based on the information that we have. So with these questions, I'd really encourage you to look at them on your own, maybe try them on your own. I'm going to work through them here, obviously, but if you find it helpful to kind of think through them on your own first, then feel free to do that. So the first thing is just filling in these values. And so we know, if we're looking at the non-smokers, actually what we know is that 38 out of 59 were smokers that had lung cancer. And we also know that 192 out of 852 were smokers that didn't have lung cancer. So then this cell right here is going to be 852 minus 192. So that's going to be 660 would then fit here because this number has to add up with 192 to get to 852. And then the total, we can kind of do the same thing here. There's a couple ways that we could do this calculation, but I'm going to do 911 minus 230 to figure out that about 681 people are missing here, which it also makes sense because it should be the sum of these two numbers above it. Okay, secondly, we're going to calculate the probability that someone in this poll had lung cancer. So this is just asking for the total number of people with lung cancer. So it's not going to be one particular cell. It's actually made the sum of two different cells, right? So lung cancer is going to be this row right here. So it's going to be these 59 people total. Well, I guess it is a cell because we have the totals over here. So it's going to be this 59 divided by the total number of people in the poll, which is going to be 911. I'm not going to calculate the probabilities to a decimal. I'm just going to leave them as they are. So 59 out of 911 had lung cancer. Calculate the probability that someone was a smoker and had lung cancer. This is a little bit more specific. So this is going to be an intersection if you want to think of it that way. So if you want to think of this as two circles where we have lung cancer, we have smoker, we have some people in the middle, and then we have people who are neither. This first question was asking for the whole lung cancer bubble, right? So it's asking for everything in here. Whereas the second question is asking for an intersection. It's asking for lung cancer and smoker, which is going to be this intersection right here. So that's going to be the 38 in that very specific cell divided by 911. What is the probability that someone in this poll has lung cancer given that they were a smoker? So for conditional probability, remember the probability of A given B is going to be the probability of A intersect B. So A and B divided by just the probability of the condition part. We can also think of it as number of people. So since we're working with frequencies, it would also be fine for us to just plug in the number of people who meet A and B divided by the number of people generally in B. So in this case, the probability or the number of people who both have lung cancer and were smokers is going to be 38 still. And we're conditioning this over the number of people that were smokers in general, which is going to be 230. And so, well, actually, I'm not going to calculate that decimal, but that would be what we're looking for. So again, the probability that somebody has one thing given that they have something else, if we're working with frequency data, we can just plug in those frequency values, and we can recognize that 38 people have both of those things, and 230 people total have the condition part. So 38 out of those 230 of those 230 smokers had lung cancer. All right. So here is a situation that I'm presenting it this way because it's a little bit different than what we saw before, but I think it's a good way to kind of think about these terms and how we can use all the information we have to find these probabilities. Let's say that we're looking at a pregnancy test where false positives and false negatives are both real but relatively low possibilities. Let's say that in a particular population, 1% of women who take a pregnancy test are actually pregnant. Let's say that 2% of women who are not actually pregnant incorrectly get a positive result. And let's say that 0.5% of women who are actually pregnant incorrectly get a negative result. Okay, so the first question that we want to know is, does the event of being pregnant and the event of getting a positive result appear to be independent events or dependent events? So let's first kind of back up for a second. What are independent events? What are dependent events? Independent events means that the likelihood of one happening does not affect the likelihood of the other. It means that these probabilities are constant in relation to one another, that if I know one piece of information, that doesn't give me any more information about the other. So let's think about what a pregnancy test is. So if I'm thinking about a pregnancy test result and the likelihood of being pregnant, do I expect those to be independent events or do I expect them to be dependent events? Well, if they're independent events, then this is really a useless test, right? So why would somebody take a pregnancy test if it's independent of actually being pregnant? So if you think about it logically, you'd realize these should be dependent events, because if I get a positive test result back, that means that the likelihood that I'm pregnant, well, maybe not me, the likelihood of this person being pregnant is going to be a lot higher than if they got a negative result. Oops. Is higher with positive result. So this one's kind of hidden, right? Because you might be thinking numerically, how do I solve this? Which we could certainly do that. We could kind of break down these probabilities, maybe put them in a tree diagram, which we're going to do here in a second, and calculate that. And maybe we should do that right now. But if you think about the context, though, hopefully you also recognize that contextually these should be dependent events. So here, we can do this in either order, but I'm going to do it the logical order, which is going to be pregnant or non-pregnant first, and non-pregnant. And then the second node here is going to be positive, negative, and again, positive, negative. I'll put that here for consistency. So we talked about these being dependent events, right? So that means that this set of probabilities right here is going to be different than this set of probabilities right here, right? So that means that if you're pregnant, your probability for positive is probably going to be a lot higher than your probability for negative, or it's going to be a lot higher for positive than it would be if you were not pregnant, I should say. Okay. So we need to fill these in. So the first question is what probability or what percentage of women in this population are pregnant? And we have that information in our first bullet point. 1% who are taking this test are pregnant. So 1% of our population is pregnant. And 99% are not. And really I should do decimals, but I already did percent signs, so I guess we'll just go with that. Okay, so we also know that 2% of women who are not actually pregnant, so somewhere down here, 2% of these women will get a false positive. So that means that we have 2% going this way, the other 98% will correctly get a negative test result. We also know that 0.5% of the pregnant women, so if we're going over here, 0.5% of them are incorrectly going to get a negative test result. So that's going to be 0.005, and this one's going to be 0.995, and I guess I didn't do percent signs on that, but oh well. Okay, So with that in mind, now that we have this tree diagram filled out, these questions are going to be a lot easier otherwise. What is the probability that a woman who takes this test will be pregnant and get a positive test result? So the probability of pregnant, and intersect positive results. Well, that's going to be the probability of pregnant times the probability of positive given pregnant. So the probability for pregnant is going to be 0.01. The probability for positive given pregnant is going to be this 0.995 value. So if we go this way, the probability for pregnant, or probability for positive given pregnant, is going to be that 0.995. And that would be let's see, this is going to be 0.00995. So not a whole lot of correctly positive results because there's just not a lot of pregnant women in this population. Okay, secondly, what is the probability that a woman who takes this test will not be pregnant and get a positive test result? Okay, so again, this is going to be another similar setup here. So not pregnant. And positive is going to be not preg times positive given not preg. So not pregnant is going to be 0.99. Positive given not pregnant is going to be that 2% value down there. So if we go this way, this conditional probability is going to be 2%. So that's going to be, let's see, let me calculate this to make sure I do this correctly. 0.99 times 0.02. It's going to be 0.0198. And while I didn't ask it here, another fair question you should be prepared for is what is the probability, or what is the probability of getting a negative test result given you're really pregnant, right? And so we could just look at that and say that a conditional probability is going to be one of these values over here. These are all conditional probabilities. So if it's asked in a way that it's just asking for a conditional probability, you're looking for one of these values. So always be kind of careful for that.